Whenever we talk about growth, I have the impression that there are a lot of different communities being engaged in this debate. You find some pro-growth, mainstream growth, green growth communities. You find some beyond growth communities, and even some degrowth communities. And to my experience, it's rather difficult to bridge this gap between these different communities and to find a language how these different communities can communicate. And we thought that system thinking and system mapping might be a good method to support a kind of dialogue between different communities. Might be researchers and policymakers, might be different worldviews, might be different logics or even different disciplines. And what I would like to give is a short tour de force through system thinking and system mapping by, first of all, talking about what do we understand by a system? What is a system? What does system thinking mean? How can system mapping be used? And how will system mapping support the knowledge brokerage, which is in the core of the Responder project? Actually, Responder is about linking communities. It's about digging out existing knowledge, transferring it, answering questions, bringing in new knowledge to policymakers and to researchers as well. So actually, what is a system? We like to use this term system for many different things. So would you say a sand heap is a system? If you have a look at a sand heap, you could say, well, that's the rather easy thing. The individual grain of sand is only loosely connected to the other individual grain, and it doesn't seem too complex. But there are some serious scientists just dealing with sand heaps and throwing individual grains of sand just on top of a sand heap, and then they wait because dropping just one more grain might nothing cause to happen. And then you drop one more grain, and this causes that the entire heap collapses in a massive slide. So these scientists, they're looking for so-called self-organized criticality. And yes, so even in a sand heap, you can find rather complex and nearly unpredictable phenomena. But however, we think that systems are normally a little bit more complex and they are able to do more than just to collapse. So let's have a look at another example. For example, the car engine. The car engine can also collapse, but normally it should, when you switch it on, it manages to keep two parameters rather constant, which is motor speed and temperature. So this is a kind of cybernetic system that keeps two parameters stabilized through rather simple control systems. This kind of cybernetic view is wonderfully expressed, for example, in a nice short story of Ray Bradbury, the author of Fahrenheit 451, in his book Mars Chronicles. In this short story, he describes how a fully automatic house on Mars dies after 20 years, that all the people left for 20 years, all the parameters were constant, but then there is a fire and it is no longer able to deal with this disturbance. There are similar science fiction stories of Stanislav Lem and Douglas Adams, for example, that follow a similar line. And I think when we have a look at the accidents of Chernobyl and Fukushima, we see similar problems. And the problem standing behind is that these technical systems can only deal with disturbances which were predictable and which they were planned for. So if we go to another view of a system, let's have a look at nature. Living systems normally can do much more, and they can be easily distinguished from inanimate nature because these systems are able to grow, they are able to repair themselves, to reproduce themselves, and sometimes even to transcend themselves. This is called emergence. Not emergency, but emergence. And it describes a phenomenon that new properties of a system emerge at a new level of complexity. These are phenomena which normally you cannot explain just out of the components the system is made of. So for example, the behavior of a cell cannot be fully explained by the atoms and molecules which are in the cell. And I think also my individual behavior or my attitudes cannot be explained just based on the functions of my cell. So we see this leads us to another characteristic of a system. You cannot explain functionality and behavior just based on components. You have to have a broader view. And the simple saying that the whole is more than its parts, it's very true when you deal with complex systems. So let's increase complexity even more and have a look at that. The crowds. different kind of crowds of individuals, groups, populations, societies, you can name them. And in biology as well as in sociology, a lot of theories have been developed to describe their behavior, just like to remind you of the very famous books of Friedrich Kappa and Friedrich Wester. I think you all know them. What you perhaps don't know is that Hans Haas, an Austrian, you know him about his famous movies on sharks, he developed the so-called Energon theory, trying to integrate natural science, social sciences, economics, humanities, and Ken Wilber, for example, in his big theory of hormones, even integrated this with spirituality. All of these big, all-integrating theories have one problem, that systems thinking on this very high level gets more and more complex as these different disciplines are involved and a great variety of subsystems have to be considered. Well, an anthill. An anthill gives me the opportunity for two little stories that I would like to tell you. One story is about Langton's ant. Langton's ant, did any one of you come across Langton's ant? Just raise your hand if you know the story. Okay, fine. You're not in mathematics, I think. You're not in artificial intelligence. I think Langton's ant is a nice example that it's very difficult for us human beings to understand the system's behavior. Just Langton's ant is a game you can play, even in the coffee break. Langton's ant follows just two simple rules. Langton's ant moves around a square sheet of paper, and whenever Langton's ant enters into a white box, it changes the white box to red, and it turns left. This is rule number one. Next step, it enters a white box, changes to red, turns left. And again, and again. So that's very easy, I think. When it enters a red box, there comes in the second rule. If Langton's ant enters a red box, it changes the red box to white and turns right. Two simple rules, okay? So it changes to red, turns left, changes to red, turns left, changes to red, turns left, and again, changes to white, turns right, and so on. How do you think the pattern will look like? If we continue with two very simple rules that I'm sure both rules you really understood, which pattern will emerge? Imagine a really big sheet of paper, okay, not just this small one, and let's say 15,000 steps, okay? What will you see after 15,000 steps? Will it be a simple pattern? Will it be pure chaos? Will it be anything in between? And I will keep this tension till Friday afternoon, so that you have something to think about. I don't want to give you the answer now. You can try it out on a computer, on a sheet of paper, either. The second story that came into my mind when I had a look at this anthill is from Douglas Hofstadter and his famous book, Gödel, Escher, Bach. It was a kind of Bible in the 1980s for all the guys dealing with artificial intelligence and all the computer nerds, because he found some similarities between mathematics, Kurt Gödel, music, Johann Sebastian Bach, and the artistic illustrations of Escher. And he illustrated these similarities in a series of very nice short stories, and one is the story of the anteater and the anthill. So the anteater visits the anthill is called Aunt Hillary, and he has a very nice conversation, philosophical debate with the anthill while he's eating the ants. And the philosophical debate goes in the way that the ants write something on the floor. So the anthill communicates by ants writing something on the floor, while the individual ant is eaten. And the anthill says, well, help yourself. I don't care if you eat 1,000 ants, it doesn't matter. And they're having a very nice debate. What can we learn from this story about systems and even for knowledge brokerage? Well, I think we should be aware that when we talk to individuals, you might persuade them, and you have good arguments for sustainable development and challenging growth, and then they go home and nothing changes. So if we want to intervene into systems, we have to think on different levels. Perhaps speaking truth to power is okay, but you speak truth to individuals. And you don't change a lot on the system, on the power, who has the power in the system, if you just persuade individuals. So let me briefly summarize what characterizes a system. It's made out of organized elements. They are in a certain relationship to other elements, and there's a relational framework, which we call system, and that's attempting to close itself as a form of unity or a whole, and it functions rather independently from its surroundings, and the boundaries between inside and outside are rather important. So now what does system thinking mean? System thinking we can differentiate from a sort of mechanistic thinking. While in mechanistic thinking we think in objects, in system thinking we think in relationships. While in mechanistic thinking we think in events, individual events, system thinking means to think in continuous behaviors. Mechanistic thinking focuses on the one hand on static snapshots and linear progressions, while system thinking is based on circular relationships, delays, discontinuities, and so on. While mechanistic thinking tends to be a sort of reductionist thinking, system thinking is a sort of holistic perception of the whole and understanding the behavior of a whole, and not just explaining it by its parts. So mechanistic thinking most of the time focuses on solving problems, but system thinking offers some insights into problems. So the benefits of system thinking is, and we offer this kind of thinking to you, because we think that in Responder it is important to mutually understand each other, that researchers understand the logic of policymakers, that policymakers understand the logic of researchers, that pro-growth guys understand the logic of degrowth guys, and not just say, oh, aliens, and the other way around. And this is why we apply system mapping and system thinking through the whole Responder project. So we think that, we hope that it makes you think differently, and that we offer a more effective way of dealing with complex situations. We provide some tools. You will experience this in the afternoon. And we hope that system thinking can acknowledge the richness and independence of real life, interdependence of life. So now what is system mapping about? System mapping is a method that we will use, and to explain it in a very easy way, I thought I'd take an example of my personal experience, and it has something to do with growth. It's just physical growth. So, and I thought, okay, my body mass just depends on two things: food consumption and physical activity. As long as these two key factors are balanced, I keep in shape. Although I like to eat chocolate cake, as long as I jog every day, it's fine. So we have an example concerning consumption and even growth. And if we take a more systemic perspective, yeah, the food consumption, what does it depend on? Well, sometimes it depends on the level of frustration. The more frustrated I am, the more chocolate I consume. The more chocolate I consume, the fatter I get. The more fatter I am, the more frustrated I am. The more frustrated I am, the more chocolate I eat. So we have a sort of feedback loop, and if we would describe this feedback loop in the terminology of system mapping, we would say if frustration level goes up, chocolate consumption goes up. If chocolate consumption goes up, body mass index goes up. And if body mass index goes up, frustration level goes up again. Positive feedback loop. So this is a kind of vicious cycle. But there was the other part influencing. This is about physical activity, so more physical activity, less weight. Less weight, perhaps emotional support of my partner. Emotional support of my partner, more physical activity. So we have a feedback loop which is the other way around, which might now balance or compensate or even compete with the first one. So we have two feedback loops in the system. So how can we steer a system now? Well, on the one hand, there might be some experts or even some policies trying to change my physical activity, telling me you should go more for jogging, practice more sports, or even some policies steering my behavior. But on the other hand, there might be some new companies producing new chocolate shots, so every time when I have a very frustrating telephone call, I can have a chocolate shot. So this might then change my habits. So again, we have this kind of feedback loop. And if we want to steer a system in a more systemic way, we could look for certain elements that change not just one feedback loop, but change the whole system. For example, if we insert values as one more key factor, these values, for example, serenity, might reduce my stress level on the one hand, and on the other hand, if I'm more relaxed, even my partner is happier. So in both loops, we have some stimuli there. Easy example, if we draw these kind of system maps in a more technical way, they look like that. On the first sight, you would not like that. It's very difficult if you do not develop such a system map in a participatory way to buy in. It's very difficult to understand, so this is why I just would like to hide it. But if we have these kind of maps, and we hope to have these maps, for example, tomorrow, on 3 specific areas, coming out of the breakout sessions, then we will be able to talk about single links, we will be able to talk about reinforcing loops, and we will be able to offer a sort of platform for you to communicate even after this event, to ask some questions, to get some answers based on a shared understanding how a system looks like. And this is what Responder will offer then on the Responder website. So how will system mapping now be used for knowledge brokerage? If we have a look at our aims of Responder, Responder aims at linking sustainable consumption and growth debates, which is tricky because it involves many different communities, at least 4 communities: science and policy making on the one hand, and research community, science and research on the one hand, and pro-growth and beyond growth on the other hand. So at least we have 4 different communities: policymakers, pro-growth, policymakers, beyond growth, scientists, pro-growth, scientists, beyond growth. Very different worldviews, very different paradigms even. And we hope that system mapping offers a sort of platform to communicate in a participatory way. Just an example, what we have in mind. I don't want to go into the details of these maps because they were not meant to explain something, they were just meant to show you something, what we have in mind. I will show you 3 times the same map, but just highlight different parts of the map to show you that within one map you could find 3 different worldviews. For example, this could be called as a cornucopian perspective, sort of mainstream perspective, where consumption leads to subjective well-being, production capacity of the economy increases consumption, and workforce mobility deregulation might increase production capacity. This is part of a bigger map, and this is one perspective. We switch on the blue light, and for example, mainstream growth researchers might find this rather okay. This fits to their worldview, and everybody's focused on growth rates of GDP. You could switch on another light, and you get a sort of ecological modernization perspective, which means that you insert, on the one hand, total material consumption and quality of ecosystems. This might affect subjective well-being, and you have one factor which might influence the total material consumption, which is technology. So this is a point of view that might fit to the limits to growth debate, for example, and we could even switch on a third light, which is then about the decommodification perspective, where you bring in, for example, social capital. Social capital influences subjective well-being, and so on. Just an example to show you that 3 different worldviews could be mirrored in one picture, and you just switch on different lights. And I have to tell you that this is not truth, this is just an example. So I don't want to discuss all of these details with you. It was just to show you what we have in mind. Big picture, at the end of Responder, switching on different lights and allowing different communities to understand how the other ones think. So what can you get out of this experience of Responder, out of this experience today and the experience in the upcoming events? You can take a broader perspective on the whole system. You can discuss potential links and contradictions between sustainable consumption and growth. We hope that this exercise helps you to mutually understand the worldviews of other participants, so that it offers a sort of platform for mutually understanding, talking to each other, but not just giving individual arguments, but collaborating in producing such system maps. We hope to bridge the gap between research and policy making. We want to try out this innovative method. System mapping has been used in Portugal, in the Netherlands, in the United Kingdom, in different areas by now. We applied for the first time on a very complex issue as sustainable consumption and growth, very general issues. And you can get out of this experience that you utilize system mapping to organize your questions and answers so that they are not punctual questions that you ask and you get an answer, but you don't know so much about the context. But the questions are answered are based on a shared understanding and a shared platform. Thank you.